Hello, my name is So Ming, and my student ID is MAT 2409043. Today, I want to talk about bounded set. We will first introduce the definition of upper bound, lower bound, supremum, and infimum. Then, we will use this definition to prove a useful theorem about the relationship between maximum and supremum. Okay, finally, we will show an example and solve it using definition and the theorem. The concept of a bound is very important. Every non-empty finite set must have a maximum and a minimum. For example, consider the set 1, 5, 10. Obviously, the maximum is 10, minimum is 1. But for an infinite set, the maximum and minimum might exist or might not exist, right? For example, the open interval 0, 1 has no maximum and no minimum. But does this mean that the set contains every real number? Obviously no. For example, 2 is not in this interval. Okay? Since a maximum and minimum do not exist, we need something else to describe the boundary of this interval. The intuitive way is to find the ceiling and the floor of this interval. We call the ceiling an upper bound and we call the floor a lower bound. First, let us define the upper bound and lower bound of a set. For a non-empty subset of real number, if there exists a real number C such that every element in the set is less than or equal to C, we say that the set is bounded above, and we call C an upper bound. Similarly, for a non-empty subset of real number, if there exists a real number B such that every element in the set is greater than or equal to B, we say that the set is bounded below and call B a lower bound. Okay, now let us recall the definition of maximum and minimum. For a non-empty subset of real number, a number is called the maximum if this number is in the set and is an upper bound. Similarly, a number is called the minimum if this number is in the set and is a lower bound. Then, let us define the supremum and infimum of a set. For a non-empty subset of real number, a number is called a supremum if it is an upper bound and it is less than or equal to any other upper bound. We also call the supremum the least upper bound. If the supremum of a set S exists, we denote it by sup X. Okay? Similarly, for a non-empty subset of real number, a number is called the infimum if it is a lower bound and it is greater than or equal to any other lower bound. We also call the infimum the greatest lower bound. If the infimum of a set S exists, we denote it by inf S. But a question is, if a non-empty subset of real number is bounded above, does it necessarily have a least upper bound? The completeness axiom states that this is always the case. From the axiom, it follows that a non-empty subset of real number that is bounded below must have a greatest lower bound. Okay, now consider a non-empty subset of real number which is bounded above. By the completeness axiom, we know that this set must have a supremum, right? However, a maximum does not necessarily exist. Okay, we're using the same example. Looking at the open interval 0, 1, it is bounded above, but it does not have a maximum, right? So, what is the relationship between the maximum and the supremum? The following theorem state that a set has a maximum if and only if it is bounded above and the supremum belong to the set. In this case, the maximum is equal to the supremum. This theorem is important because it helps us to determine the maximum and supremum immediately when we find one of them. Later, we will show how useful the theorem is with an example. Let's prove this theorem. Okay, first we prove the forward direction. Assume that S has a maximum. Let us call this maximum C. By definition of maximum, C is an upper bound. Therefore, S is bounded above. By completeness axiom, sup S as it, we want to show that sup S is equal to C. The idea is we show that sup S is greater than or equal to C, and then we show that sup X is less than or equal to C. Okay, first, since C is an upper bound and sup S is the least upper bound, sup S must be less than or equal to C. Okay, then since C is an element of S and sup S is an upper bound of S, C must be less than or equal to sup S. So sup S is equal to C, and since C is in X, it follows that sup S is also in S. Now, let us prove the reverse direction. Assume that S is bounded above and sup S is in S. Okay, since sup S is in S and it is an upper bound of S, by the definition of a maximum, sup S is the maximum of S. This complete the proof. The infimum version of this theorem is straightforward. Okay, this theorem states that a set has a minimum if and only if it is bounded below and the infimum is in the set. The proof is similar to the theorem we proved just now, so we will omit it. Now, let us see an example of how this theorem works. Consider the set containing all positive rational number of the form 1 over n, where n is a positive integer. We will try to find the maximum, minimum, supremum, infimum if there exist. Here is a graph of this set. From the graph, we see that the element approach 0 as n get larger and larger, but they never actually reach 0. Based on this graph, we can guess that the maximum is 1, the supremum is also 1, the infimum is 0, and the minimum does not exist. First, let us show that the maximum is 1. To do this, we use the definition of a maximum. This means we want to show that 1 is in the set and it is an upper bound. And we notice that when n equal to 1, 1 over n become 1. So 1 is in the set. Also, since n greater than or equal to 1, we know that 1 over n must less than or equal to 1. This means every element in the set is less than or equal to 1. This shows that 1 is an upper bound. Therefore, 1 is the maximum. Since the maximum is 1, by theorem 1 we proved just now, we know immediately that the supremum is also 1. Now, we want to show that the minimum does not exist. To do this, we assume that there exists a minimum and try to find a contradiction. If a minimum exists, it can be expressed as 1 over n for some positive integer n, since minimum is an element of the set. But we notice that 1 over n plus 1 is also an element in the set, and it is strictly less than 1 over n. This contradicts the assumption that 1 over n is the minimum. Therefore, we know that the minimum does not exist. Finally, we want to show that the infimum is 0. To show this, we use the definition of infimum. First, we want to show that 0 is a lower bound. And then we will show that any number greater than 0 is not a lower bound. Since n is positive, 1 over n is always positive. This means every element in the set is greater than 0. So 0 is a lower bound. Okay? Then we want to show that any number greater than 0 is not a lower bound. Assume for the set of contradiction that there exists some number c greater than 0, which is a lower bound. By the Archimedean property, we know that there exists some positive integer n such that 1 over n less than c. And we notice that 1 over n is an element in the set. This means we found an element in the set that is smaller than c. This contradicts the assumption that c is a lower bound. Therefore, no number greater than 0 can be a lower bound. So, 0 must be the greatest lower bound. Notice that 0 is not in the set, so we also can find the infimum first and then apply the theorem to conclude the minimum does not exist. This example is consistent with our theorem 1 and 2. Since the supremum is 1 and it is in the set, the maximum obviously is 1. Then we found that the infimum exists, but it is not in the set. So by theorem, the minimum does not exist. Okay, so in conclusion, if a non-empty subset of real number is bounded below, it must have an infimum, but a minimum does not necessarily exist, just like in this example. Similarly, if a non-empty subset of real number is bounded above, it must have a supremum, but a maximum does not necessarily exist. For example, the open interval 0, 1 has a supremum of 1 but does not have a maximum. Okay, so that's all. These are my reference. Okay, these are my 3 reference. Thank you.